Hello everyone. This is just a short video to supplement the understanding for Chapter 11, Integration, in particular Subchapter 11.2. In Edexcel's book, when you're integrating a function not of x, but of, for example, ax plus b, it will tell you to do so, or recommends to do so, I probably should say, by adjusting the constant. But what I want to show you here in advance of when the book does it is the power of using a u-substitution for this. In the notes and in the main lesson, I don't go into this in much depth in order to just get on with the legwork and the main practice. So this is just supplemental for those that need or want a bit more understanding of why it works, and also a few more examples to get you into the frame of thinking of how to actually use the method. So first of all, why it works. So let's consider we want to integrate a function of ax plus b, and this function itself may be, in fact, to the power n. So let's set out the problem. Let's imagine we want to integrate this thing here. So integrating a function of ax plus b to the power n. So let's just write this down first of all. So integrate f of ax plus b, all of that to the power n. That in itself looks ugly. So let's just imagine here that we make a substitution. So if we say let u equal ax plus b, this is the substitution. We're going to take off ax plus b and put on u. So if we do that, we can actually differentiate u with respect to x. So du by dx simply becomes the derivative of what ax plus b is. If we differentiate this, we're just going to get a itself. Obviously the constant b will disappear. Rearranging this, we can then deduce and see, multiplying by dx and then dividing by a, that dx is going to be du over a. And just reminded me here, I should have put in this as with respect to x. So how to integrate this? So what we can do here is make these substitutions like I'm saying. So rather than have a function of ax plus b, if I'm letting u be ax plus b, I can transform this now into simply the derivative of the function of u to the power n, of course. Fun, that's quite a, it's just me being very silly, fun, fun, lovely. And then dx, well dx itself we can substitute because now our variable isn't x, we've replaced it with a variable u. And so dx is du over a. So if I just replace this now, I can say this is now multiplied by du over a. And of course, because a is a constant, what we can do is take this 1 over a to the outside. So we can say it's the same as 1 over a integral of function of u to the power n with respect to u. And this here is often a much easier way of doing it. And so all I'm saying here is we can switch from this and use this instead by just essentially switching ax plus b and replacing it with u. The book also will only say how to integrate a function of ax plus b assumed to the power 1. This will work for more powers if the function is applicable. So for example, it might be that n is 2, 3 or 4. And so I'm just going to give you a quick rundown of when this can be used. Okay, so we can use it, useful always, when n equals 1. It's useful if n equals minus 1 and f ax plus b is just simply ax plus b. So if there's no function, but it's just simply just a linear function in itself, this is quite powerful and can be used that way. And it can also be useful if n is greater than 1 and the function of ax plus b is a exponential function. Otherwise, it's only really useful when n is 1. So just to show you that it is more useful than just n being equal to 1, you can apply it as well when n is minus 1 and sometimes when n is greater than 1. But when n is greater than 1, that's only really useful at this stage when we're considering exponential functions. That's for theory, so let's see this in practice. The upshot is, all we're doing is switching ax plus b for u and then changing the dx into terms of du. So let's try a few examples, then you can try some on your own. Let's imagine here we're integrating e to the 2x plus pi with respect to x. So first of all, we're going to switch out this 2x plus pi with u. So let's call u as 2x plus pi. We can then differentiate u with respect to x, so du by dx just becomes 2. So therefore, dx is just going to be du divided by 2. So therefore, this integral now gets transformed into e to the u, because of course we called u 2x plus pi, and then dx we can say is the same as du over 2. We can now take this half to the outside because it's a constant, and then just integrate e to the u du. Then, remembering some of the fundamental properties of the exponential function, if we integrate e to the x, or e to the u in this case, with respect to the same variable, we just get itself again. So it's just going to stay as e to the u. So that'll become half. E to the u will integrate to itself, of course, plus c, and then always replace it with the original variable. That's what the examiner will want to see. So actually u was initially 2x plus pi. So replacing u of what u actually is, we have half e to the 2x plus pi, plus of course the arbitrary constant of integration. Let's try one more. This time we've got 3x plus 1 to the power 5, all with respect to dx. So this time, again, we're going to call u 3x plus 1. So if u was 3x plus 1, du by dx will just become 3. So in other words, dx is just going to be du divided by 3, or du over 3. So then this integral, instead of 3x plus 1 to the power 5, it just becomes u to the power 5. And then the dx we replace with du over 3. So just to clarify what's happening here, 3x plus 1 has just been replaced with u, and dx is the same as du over 3. Now that 1/3, in the same way as the first example, we can take to the outside of the integral and just call it 1/3 of the integral of u to the power 5 du. And of course, if we're integrating u to the power 5 with respect to itself, we just add 1 to the power and then divide by the new power. So it's going to give us 1/3. So then the new power, when we integrate, becomes 6. So we do 1/6 u to the power 6 plus c. But of course, we weren't talking about u initially, were we? So I'm going to try and move this now. I've not left myself enough space, which is a bad habit of mine. I never seem to learn. But now, 1/3 times 1/6, we can say it's just 1/18. U was 3x plus 1. So replace u with what u actually is in terms of x. That's to the power 6. And then plus c. One more, and then I'm going to let you try some on your own. So integrating sine to the 4x minus 3. So again, we're going to call this thing here our u. So we're going to substitute this with u. And then from that, we're going to find what du by dx is. So du by dx gives us 4. And so dx is just 1/4 of du. So now if we plug this in, this integral here simplifies to sine of u multiplied by dx, but dx is just du over 4. So again, just colour coding what's happened there. dx is 1 and the same as du over 4. That 1/4 is a constant. Take it to the outside of the integral, and we get sine u du. Now we need to remember what sine integrates to. I always think about it in terms of what sine differentiates to. Sine differentiates to positive cos. Then I think of it, if sine differentiates to positive cos, sine integrates to negative cos. So when we get 1/4 minus cos u plus c. But of course, u was 4x minus 3. So then we just put that back as it was. So it's minus 1/4 of cos 4x minus 3 plus c. So that's how you do it, essentially. That's the general pattern, the general way of doing these things. Now try some of these on your own. I'll give you a few pointers for the first one. What you might want to consider here, consider 1 over 4x minus 1 as being the integral of 4x minus 1 all to the power of minus 1. And for this one here, I put it in red because it looks a bit harder, but just switch u with 3x plus 2. So switch 3x plus 2 for u. So pause now if you want to, and then press play when you're ready to see the solutions to these, and hopefully yours will match mine, and if so, you know you've got this strategy almost mastered, or at least beginning to. Okay, so let's see the solutions. So the first one, let's call this first of all the same as 4x minus 1 to the minus 1 dx. So we're going to say u as 4x minus 1. So then we take du by dx, differentiate 4x minus 1, that just gives us 4, and so dx will be du divided by 4. So putting these in, this integral here, we switch the 4x minus 1 with u, so it now becomes u to the minus 1 multiplied by dx, but of course, sorry, not multiplied by dx, with respect to dx, but dx is the same as du over 4. So replacing the dx with du over 4 gives us this. That 1/4 is a constant, so it can move to the outside. And then we're just integrating u to the minus 1 with respect to u. You can leave it as u to the minus 1, but if I put it as 1 over u, that might spark your memories. If you integrate something to the power minus 1 or 1 over u with respect to itself, that will integrate to the natural log of the modulus of u. And so that's the final step. So we say it's the same as 1/4 of ln mod u plus the arbitrary constant of integration. Final step, replace u with what u actually was in terms of x. U was 4x minus 1. So it's 1/4 natural log of the mod of 4x minus 1 plus c. The next one, cos to the 5x plus 1. Again, we're going to say u is 5x plus 1. And from that, we take du by dx, differentiate 5x plus 1 gives us 5. Then rearrange this, multiplying by dx and then dividing by 5, essentially. You can think of it as being, we're going to have that dx is just du divided by 5. So then we can transform this beast into a better looking one, or at least one that looks, in my opinion, less intimidating. So this integral gets transformed now to cos of u multiplied by not dx now, but du over 5. So then replacing u So you're replacing 5x plus 1 with u, and dx is, of course, du over 5. You're probably getting the hang of this now, slowly but surely. That 1/5 we can take to the outside of the integral. Then we have cos u du. So cos integrates to sine, so you still need to know some of the standard results. This u sub is helpful, but it won't solve every problem. We still need to use our logic and memories. So that goes to sine u. So we're going to get 1/5 sine u, plus, of course, the arbitrary constant of integration, plus c. Final step, replace u with the original variable, which was in terms of x. So it's 1/5 sine of 5x plus 1 plus c. Always remember the plus c. You will not do yourself any favours by forgetting the plus c. Finally, this one, which looks probably nastier than what it actually is. So what we do here is we say u is 3x plus 2, and therefore differentiating u by respect to x, we get 3. So from that, we can hopefully see that dx is du over 3. So we're just saying that 3x plus 2 now is our u function. So we're going to transform this into the integral of e to the u all squared times dx, but dx is now du over 3. Again, that third we can take to the outside. E to the power u to the power 2 becomes e to the power 2u with respect to u. And then we can integrate this using our knowledge of how we integrate exponential functions. So we're going to have 1/3, because it's e to the 2u integrating, that 2 will come to the front, and we're going to divide by it. So we get a half e to the 2u plus the constant of integration, c. Then neaten up and replace u with what u was in terms of x. 1/3 times a half is 1/6. E to the 2u, well, if 1u was 3x plus 2, double that, we get 6x plus 4. Then, of course, plus the arbitrary constant of integration. And that's the general format of how to use this u sub. So why have I shown you this? Two main reasons. It's an alternate method to what the book introduces in chapter 11.2, but as well as that, because u-substitutions are a subchapter and a skill in their own right, I think now is a good opportunity to introduce them as early as possible. So when you come to the chapter of using u-substitutions, you're already a bit more familiar with this idea and how it can be used. Well, thank you for listening. Hope that's helpful to an extent. Join me for the next video. Take care.